Okay, last question. So reaction that you've done, it's all about a reaction you've done, but I'm not expecting really that you would have learnt this equation. You'll simply remember this as the disappearing cross experiment in most cases, I'd have thought. And you remember you did the reaction maybe in a flask or a little beaker, and you'd be peering through the top of it and you'd see a big fat cross disappear. And the reason the cross disappears is because it's producing this reaction with this chemical called sodium thiosulfate and acid. Produces some sodium chloride, which is a soluble salt, water, which you won't even see, a little bit of gas, but that stays dissolved. But the issue is you produce sulfur, which is a precipitate, a solid, and that's why you can no longer see through it. But what's the question about? So the question is around the mass being greater at the start than the end. And the reason why the mass was greater at the start is because you're producing sulfur dioxide gas, which of course is going to escape, and so the mass is going to decrease as the sulfur dioxide escapes. Okay, so you get a mark for saying sulfur dioxide produced, even though it's telling you, or you could simply say or gas is produced and which escapes. If it's escape, you're no longer measuring those atoms. The atoms of sulfur and oxygen that were in the reactants are no longer in the flask. That's why the room gets a bit smelly when we do this one, and we should always leave the windows open. Right, so the teacher demonstrated the reaction. Hopefully you guys did it yourselves. You've got a stopwatch, conical flask, the cross there, and you can start to see it fading in this picture. We've got a method here all set out, which I'm sure you read. So what type of variable is time? This is stuff that you knew way back in year 7, but maybe you've forgotten because it's been a while. But just go through them quickly. Controls are the things you keep the same between different experiments, so ain't that. The independent variable is the thing that you're changing between experiments, say the concentration or the temperature. And so the thing that you're measuring is the dependent variable, and that's what's going on there. The next one, you've got to draw a graph of these results. So happily it's done the table for you. It's got the time up here in seconds, given the units as well, the temperature in degrees C. So I'm just going to do that quickly. So the temperature in degrees C, I'm going to start at the top, so 82 seconds, which is here. Each square, by the way, is 2 seconds, and that's 19 degrees, so there's 19. Again, each square is 2, so we've got 82 and 19. That's my first one. Good practice to draw a nice little cross there so it can be easily seen by the examiners and it's scanned in. And the next one is temperature is 32, on that line, and times 48. 43. There. Just going to pause the video and do these quickly. There we go, quickly plotted those, so you don't have to listen to me waffle through that. So you get a graph like so. This is clearly not a straight line, this looks like a bit like a curve to me. So you get 2 marks for plotting correctly, and you get 1 mark for a line of best fit. I would say that's looking like a curve, so I'm just going to draw a curve. Like this, and I'm going to ignore the anomalous data point there, and that's what I would have drawn that graph. Okay. Helpfully, they've drawn a very similar one over the page, so it gives you an idea of what you should have done. Slightly better than the one I drew. Right. So, student investigated the effective concentration of sodium thiosulfate, and exactly the same sort of thing. So, as the concentration increased, time taken decreased. If you've got a graph like this, you can use a tangent to work out the rate, and you've got the tangent drawn here for you. Right, so you should be able to draw a tangent yourselves, by the way, and that comes up quite a lot. So all a tangent is a straight line matching up with the steepness of the graph at any time point, so there or there or there or whatever, and this one happens to be drawn nicely for you here, you have to work out the gradient of this one. So the way you normally tell me you've been taught this in maths is rise over run. So the way to work out the rise is it's best practice to draw a line like there up to here. So the change in y, remember each square is 2, so 4, 5, 6, 7, 8, 9, 10. So change in y is 10. And that's all the way from 0.1 to 0.6, which is 0.5. I'll just pause the video quickly there just to show you where I've got the 10 from. So it's the difference between 15 and 5 is 10, and 0.6 and 0.1 is 0.5. So 10 divided by 0.5 is the same as 10 times 2. So that's 20. And the units are kind of tricky, right? So it's the units are, if I tell you what they are to start with, it's 20, and the units are seconds, decimeters cubed, mole to the -1. So where does that come from? Let's say, well done if you work this out. I'm trying to think of the best way of showing you this. But let's write out that equation again. So 10 divided by 0.5, and I'll write the units next to it. So the units were seconds divided by the units for this one, mole per dm cubed, right? So if we tried to get all these on the line, so we could say, by the way, 1 over mole per dm cubed, it's the same as writing dm cubed per mole. So that's equivalent to seconds, because that's staying where it is, dm cubed per mole. I think that's quite, oh, you can't see any of that, brilliant. So I'll just go through that again. So if we write out the equation again with the units, seconds at the top, moles per decimeters cubed down here, because these are the denominator at the moment. If you make them, bring them to the top, both of them are flipped, because 1 over mole decimeter cubed is the same as decimeters cubed per mole. And so you end up with those as the units. So if you got that one right, really well done. That's a very good effort. So we're getting there. Question 3.5. The student determined the rate of reaction at regular intervals. The rate decreased during the reaction. We know that because the graph got shallower. So at the start here it's very steep, and at the end it's very shallow. A very common question, it was in the triple paper as well, something very similar to this. And that's because the reactants are used up. So we've got to think about the consequences of that. The reactants are used up. So concentration decreases. Specifically, it is of the sodium thiosulfate. But as long as you're clear that the number of particles per unit volume or the concentration decreases as the reaction proceeds, you get the first mark. And therefore the frequency of collisions decreases. So it's just a concentration versus rate thing. Very common that as a reaction proceeds it slows down, and it slows down because the reactants are used up. And I think that's the end of the paper. So there we are, hope it went okay.